Good evening, everyone. Hey, guys, are you there?
Good. Whoa, good evening. Hello there, Rich.
I'm here.
Don, Gerald.
I'm
Good.
here.
Everybody's here.
And looking on Facebook, we have visitors from all over the world here.
Yes.
Oh my gosh.
Thank you all for chiming in on where you are, because we have quite an eclectic group tonight. International, multinational.
Yeah. How'd we work that?
Yeah. So I guess, guys, we have to explain why we're a virtual program tonight. And we're experiencing a very rare event here in California, rain. So it's not a very good night to open the domes for the telescopes, but it is a perfectly good night to talk about the latest events in astronomy and to show you some photographs of the night sky that we have taken through our telescopes.
That we would have looked at tonight.
And that we would have looked at tonight if it hadn't been for the rain.
Yeah.
And so that's the plan. So where are we starting?
Oh, I don't know. Let's see. We have an eclipse coming up. So why don't we start talking about that? On the night of May 15th, which I believe is a Sunday night. Yep. I've been having a lot of trouble matching dates and days. So check me on this. You know,
okay.
May 15th,
Sunday night, May 15th.
Sunday night. There will be a lunar eclipse. A lunar eclipse happens when the moon passes through the shadow of the Earth. And for those of us here in the Bay Area, the eclipse will already be in progress when the moon rises in the evening. But the moon is going to slip through both the penumbra and the umbra. The penumbra is the outer part of the Earth's shadow. It's kind of faint, so doesn't seem to actually cause the moon to get darkened very much. But then when it slips into the umbra, which is the inner part of the shadow, the moon gets pretty dark and turns that rusty red color. And that is coming up on May 15th. Rick, I think you've got some images of a previous eclipse here to give people some idea what to expect.
I do, Gerald, and let me minimize this and hopefully right now this was rehearsed beforehand, but this is live. Anything could happen.
Anything could happen. Yep.
Are we seeing this?
No, we're not. No.
All right, this is okay. Let me stop.
Yeah, you gotta open the photo in the photo editor and then share.
Well, that's exactly what and now it's not letting me stop. Okay, so let's.
There you go. Now you're good.
All right, so we'll do this one more time. All right, so there it is. It's in the photo editor. And there is the picture. All right, now that should be loading.
It's not there.
Oh well. Where's the understudy?
yeah, really.
Lost my connection. I got hit by a moonbeam. Okay.
Yeah. Oh well.
All right. Give it another try here.
All right. All right. Let me make sure.
While you're doing that, I'm going to see if I've got any that we can maybe share here, just in case.
Okay. So you look for that. All right. I'm gonna double click.
All right.
Now this photo is open. I can see it's open. It shares screen.
Hey, there we go.
There we go.
You're kidding me. We actually have it this time?
Yeah, but it's not the eclipse. It's Nellie.
Well,
that's
that'll be coming up here.
Yeah,
it's a start.
It is a start. Yeah.
So actually what we're looking at here, we've kind of torn the curtain aside, and you're actually seeing what it looked like up at Chabot last May. And that very large telescope is our very own Nellie, our 36-inch Cassegrain reflector. And while it is the ultimate instrument for looking at deep space objects, we had to make alternate arrangements. And as you can see on the telescope, there are two finder scopes. And this is what we had our camera connected to. So here you can see under the large Cassegrain telescope, a little finder. And that is a camera connected to the finder, which was providing this image right here. So this is the eclipse at maximum in the San Francisco Bay Area. And I don't have a timestamp on this, but I believe it was about 4:12 or 4:20 a.m.
And this was on the 26th of May, right?
I'll take your word for that. I don't have the
Well,
timestamp.
I'm reading the label on the image.
Oh, good. I can't see it. Oh, there it is.
Yeah.
Okay. Yeah, this is good. So this is what happens when you don't use Zoom for about a month. You kind of forget where the labels are. At any rate, we found the picture, and this is what we hope to see this coming May the 15th, I believe.
Right.
And so when the moon rises, as Gerald mentioned, the moon is already going to be in partial eclipse. This represents the fully eclipsed moon at that time last year, and we hope to see this again. And it will be visible here in the Bay Area from virtually anywhere. And it's going to be rising in the east at about, I think it's a little after 8 p.m. and goes into full eclipse around 9. We can get the exact details on that.
Yeah. So it will be partially in eclipse as it's rising. Now, I'm sure everybody has heard about the blood moon, and you see why they call it the blood moon. It's kind of a rusty red color, and that's because the Earth is blocking the sunlight that would otherwise shine on the moon. But because of the Earth's atmosphere refracting light, basically, if you were on the moon looking back toward the Earth, you would see a red sunset all the way around the circumference of the Earth. And that red light, which is being refracted and filtered by the Earth's atmosphere, is filling in the shadow of the Earth. And that's producing that red color that you see. So you're just seeing a red sunset as seen from the moon.
Hey, Gerald, we just got a question. Will we be doing a live stream for that event? And the answer, unfortunately, is no, we won't.
Yeah, I don't think so.
We will be. We will have an event at Chabot, I believe.
At Chabot, right? Yes. We are going to be opening up our observatory plaza that night. I believe you're going to have to buy tickets. I'm still waiting to hear the word for that, but we will be opening it up and let you come up, and we will have one of our telescopes pointed at the moon. Of course, you can see all of this with your naked eye, so you don't need a moon. I mean, you don't need a. Yeah,
no,
you
do
You
need a moon.
do need the moon. The moon is
but you
required.
don't need a ticket.
You don't need a telescope. Yeah. So something to look forward to. And in reality, you don't have to come up to Chabot to see this. If you're anywhere where you can see the moon at sun or at moonrise, you should be able to see this that evening. Now, of course, we say it's the evening of May 15th for those of us here in California. I understand we have some people from all over the globe joining us tonight, so you may need to adjust your time accordingly. East Coast, it's going to be, they'll actually be able to see the start of this. And the eclipse will continue after midnight for them. And then, of course, in Europe, it's a different story again. So you
check
have
your local listings.
Yeah.
Yeah. Yeah, there's a good website you can go to, timeanddate.com, and you can get information on solar, lunar eclipses in your city across the United States, and I believe they even have global locations listed. For the San Francisco Bay Area, we're going to see moonrise at 8:06 p.m. And as Gerald mentioned, the moon will be in partial eclipse. And you'd be looking east-southeast at an azimuth of 114 degrees. So if you know where east is in relationship to your home or location, it's just a little to the west of that. 114 degrees azimuth, you'll see it rising. Total eclipse begins at 8:29 p.m. 8:29 p.m. and that is Pacific Daylight time, daylight savings time, and that is for the San Francisco Bay Area. Now the moon is going to be fairly close to the horizon. It's only going to be about 3 degrees above the horizon when total eclipse begins. At 9:11 p.m., we'll have maximum eclipse, and here the moon is closest to the center of the shadow, and the map direction for that would be look southeast, and it will only be about 10 degrees above the horizon. So this is going to be very low, and that means if you are in an area where you have hills, low hills in front of you, that's probably not a good area if the view is going to be towards the east or southeast there. And then finally, for the Bay Area, the eclipse will end at 9:53 p.m. Here in the San Francisco Bay Area. And when the eclipse ends, the moon will still only be about 16 degrees above the horizon. And last bit of information, 10:55 p.m., that's when the partial eclipse ends. And again, the moon will only be about 23 degrees above the horizon. So you got to look low, but you can't miss it.
Yeah, yeah. And now, if you've been watching the moon here lately, like within the last few days here in the Bay Area, the moon is very high in the sky. So you might be asking yourself, well, why is it going to be so low in May? And that has to do with the orbit of the moon and the angle of the orbit relative to the Earth's equator and the Earth's path around the sun, what we call the ecliptic. Because the moon does not orbit directly over the Earth's equator, sometimes it can be very low, even at full moon, and at other times it can be very high. It can be almost straight overhead at times, and then at other times it can be barely more than about 25, 26 degrees above the horizon. So there's quite a variation in how high the moon is above the horizon on any given night throughout the year. And again, that's because the moon's orbital path is neither over the equator, nor is it directly over what we call the ecliptic, which is the line, the imaginary line caused by the Earth's orbit around the sun. So anyway, coming up, the lunar eclipse on May 15th. Okay. So, all right.
Rick, we had someone ask if you could repeat that website again. I'm guessing they're talking about the date and time website.
Yes, it's time and date, all one word, timeanddate.com. And from there, you can select eclipse and then select your location. It's pretty explanatory once you get to the website, timeanddate.com.
Richard just put that in the chat, so that's good.
Thank you, Richard.
You're welcome.
So once you stop sharing that image, and we can talk about something else. Somebody asked on YouTube, am I out in space? Well, it kind of looks that way. I am in orbit right here. There's the Earth right here orbiting over or circling over my shoulder. Actually, just got an image behind me. But what I wanted to do is talk a little bit about a recent announcement about the farthest star that we've ever seen. And some of you may have already seen the news about this, but if I could share my screen here, I'll see if I can find this image. Hopefully I got it here.
Oh,
See that?
yep.
Yep.
Yeah, except that I want to bring it up here.
Lots of galaxies. My gosh.
That didn't work. Oh, there we go. All
No,
right.
you're sharing it. Yeah.
This'll work.
Okay.
Can you see that now?
Yes.
Yes.
All right. Oh, I see what's going on here. Strange mode here. Okay. So anyway, yeah, hang on just a second here. I got to change.
You're in slideshow mode there, I think.
Yeah. I want to be in slideshow mode, but I don't want to be.
Well, if you want to be showing the slide in the slideshow mode, you have to start slideshow before you do the screen share. You can't enter slideshow mode while you're already sharing.
Can't.
No.
Okay. Let me.
Folks, we really do know how to do all this.
Yeah,
It's
yeah,
just been a while.
we've done this
Yes.
before.
We're actually better at operating telescopes
Yeah.
than we are Zoom, but that's
right.
another
Gerald,
story.
this is fine, and we'll get your point across. So
Okay,
I think
well-
it's,
Well, let me just. If you notice, there's this arc that you see in this image. This is a Hubble Space Telescope image. And you can see lots of galaxies. This is a long exposure looking at a region where there's a lot of very far away galaxies. These galaxies are literally, in some cases, billions of light years away. And you see that long kind of reddish arc. That's called gravitational lensing. And what's happening is there are some very distant galaxies. And beyond those, there are other stars and other galaxies. And the somewhat closer galaxies, as the light from the farthest galaxies passes by the closer galaxy, the gravitational field of that closer galaxy actually bends the light and produces this arc that you see, which is called gravitational lensing. And this can happen a lot of different ways. But what it does is it can either smear out the light from the other galaxy or the other stars, or it can concentrate them into several different images and so on. So, this caught their attention. But then when they started analyzing this part of the image and started looking at what's called the redshift, or the Doppler redshift of the light, by using the redshift and measuring how much the light is redshifted, they can actually tell you how far away the object was when it emitted that light, or at least how far the light had to travel to reach us. And
Gerald,
yeah,
can you use your cursor to show
I
exactly
can.
where? That works. If you could draw where the red line is, that is the streak of that star, that would be great.
it's
It's right
stand
there.
by.
Yeah.
Stand by. So I got one more image to show you here.
Oh, there you go.
Oh, that's better.
Oh,
Yeah.
better, yeah.
So now I'm zoomed in on that arc, and this star right there, which they have named Arundel, is a star that turns out to the light from it traveled 12.9 billion years through space to reach us. So that works out to be a distance of 12.9 billion light years away. Now, a couple of things that you keep in mind. First of all, the universe is only 13.8 billion years old. So we're looking way back at one of the very first stars to have formed after the universe formed. But the other thing that you got to keep in mind is that all during that 12.9 billion years that this light was traveling toward Earth, the universe was expanding. So this star is no longer 12.9 billion light years away. It's probably more like 40 billion light years away. It's just that it took so long for that light to reach us. So this turns out to be the most distant star that has ever been imaged to date using the Hubble Space Telescope or any kind of Earth-based telescope. This has the distance record to date. However, in a couple of months, the James Webb Space Telescope will be fully operational, and it will easily be able to see that far away. So this is the record holder for now, but stay tuned. All right. Okay, I think that's all I got. Yeah, right there. All right. Okay, so that's it for the most distant star so far imaged by any telescope.
Ron has a really good question. Would that star be extinct at this point, since it's now?
Yes.
Probably, yes.
Most likely, yeah. Especially those early stars, they were often very massive, and massive stars don't last very long compared to our sun. You know, our sun right now is about 4.5 billion years old, and will last at least another 5 or 6 billion years. But our sun is a relatively low mass star, and stars that are low mass last a long time, whereas stars that are high mass, and a lot of the early stars were high mass stars, those stars only last a few 100 million years. So yes, most likely this object is probably not there anymore, but where it was, or whatever's left of it, is way more than 12.9 billion light years away now. All right. Okay, so let's see, what else do we have to talk about? I think we were going to discuss some of the things that we would have looked at tonight if we could have. So Rick, well, first of all, let me say this. We're getting into the time of the year where there are a lot of galaxies in our night sky. This varies from time to time over the course of the year. If you imagine the galaxy, the Milky Way galaxy, is a flat disk with a central bulge in it, you'd find our solar system rather about halfway between the central bulge and the outer edge. But relative to the disk of our galaxy, the plane of the orbits of our planets are at an angle. And because of that, during certain times of the year, the sky overhead is full of stars because we're looking into the Milky Way. And then at other times of the year, we get to a point where at night, we're actually looking outside of the Milky Way. And that's when we get to see a lot of stars. And we're sort of into that, or I'm sorry, a lot of other galaxies. Thank you. And we've gotten into that period. So we are now able to see a lot more galaxies than we could, say, in the middle of summer, or say in August or July, or back in January. So now is the time to be looking at galaxies, and we've done that over the years with several times with our telescopes. Rick Taft, I think, has an image that he wanted to share, or do you want me to do it, the M104 one?
Yeah, actually, I don't have it loaded up here. I think you said you had it. So
all right, well, let me grab it then. Hopefully it's going to share here. Okay.
There it is. Yeah.
There it is. All right. So this is called M104. It's also known as the Sombrero Galaxy. And this is a spiral galaxy with a rather large central bulge, which tells us that it has a large black hole at the center. We can often tell how big the black hole is in the center of a galaxy by how big the central bulge is and how much the galaxy flexes out. Now you see this dark band here. That's actually a dust lane within the disk of the galaxy, and dust lanes like this, gas and dust like this, is where new stars are forming. So new stars are forming mostly in the disk around the galaxy, you can't see it very well, is a region we call the halo of the galaxy. And that's where a lot of old stars can be found, including globular star clusters. There's quite a few of them, actually. We can't see them in this image, but there's quite a few globular star clusters around the Sombrero galaxy. But this is an image taken with our telescope at Chabot, the 36-inch reflector that we call Nellie. So, Rick, any comments you want to make on this?
This was taken about a year ago, actually, April 17th to be exact. And so Gerald is absolutely right. This is would have been one of the targets we would look at tonight had the weather cooperated.
Yeah.
Yeah. But it's a really interesting galaxy. So we imaged it, but actually Rich Ozer and I processed that data. And what's kind of amazing, and Nellie, our 36-inch Cassegrain, is really an amazing telescope. That was a total of about 10 minutes of light data. So it's 13 45-second images for less than 10 minutes to bring out the detail that you just saw in that galaxy.
Yeah.
Very cool.
I have another image I'll share. Yet another galaxy. I am trying to find my cursor. It's disappeared again.
Oh, no.
Oh, there it is. All right.
Technical problems.
Yeah, I don't know what it is.
Yeah.
I've been doing this for 2 years and never had this kind of a problem. All right. So this is another galaxy. We call it the Needle Galaxy. And it's a galaxy that we are again seeing edge on. And notice in this case, it has a relatively small central bulge. That tells us that this has a much lower mass black hole at the center of the galaxy. But again, you can see the gas and dust lanes along here. And this is a little bit of an older image taken, I believe, in 2014. But again, this was taken with our 36-inch telescope.
Might point out that the stars that you can see there are not from that galaxy. They're in our galaxy, but
Right,
just in the foreground.
Right.
Yeah.
These are actually stars within our own galaxy. We cannot, with our telescope anyway, we cannot make out individual stars in other galaxies unless they happen to be supernovas.
Hey, can I show you another shot
Sure.
of the needle?
Sure.
Yeah, hold on for a second. Let me
While you're
get
bringing
this
that up, Richard, there's a couple of questions that have come up. I thought I'd run them by. One is a really good question for Gerald. This goes back to your description of the sun's age. How do we know that the sun will last that long? It's a good question.
Oh boy, yeah, it's a complicated answer.
Right.
Yeah, I know. No quick answer on that one.
So for decades, astronomers have been observing the night sky, and they have been able to characterize a lot of stars that are relatively close to us. And so there are different techniques for measuring the distances to stars. And one of the most reliable techniques is what we call trigonometric parallax. We take an image of a star, say in June, and then we take another image of that star in December. During that 6-month interval between them, the Earth has made one half of an orbit around the sun. The Earth is 93 million miles away from the sun. So when you do this, since you're halfway around on the other side of the sun, you have a baseline between these two images of 186 million miles. And because of that huge distance, if a star is close enough, there's a slight difference in the angle that we see the star at. When we point our telescope at the star in June, it's at one angle. If we point it at that star in December, it's at a slightly different angle. The difference between that angle, or the angular difference between those two, is the parallax to the star. And it turns out, using trigonometry, it's a relatively simple calculation. You can use that to calculate the distance to a star. So using that technique, we've been able to measure the distances to stars that are within a couple of hundred light years of the sun pretty well. There are literally thousands of stars in that range. And by looking at all these different stars and studying their temperature, we can determine their temperature based on the color, and studying their brightness and studying their chemical composition. And if they're binary stars, we can actually measure the mass of these stars. Combining all that data, we're able to produce a model, if you will, of how different stars at different masses evolve, how long they live, and how long it takes for them to reach the end of their lives. We then take that information and we look at more distant stars, and we start matching up what we can measure. We can measure the color, and therefore the temperature. We can measure the chemical composition. We can measure how bright they are or how bright they appear from the Earth. And we start plugging all those numbers into this model, and it tells us where the star is in terms of its mass. And based on the mass, because we know how long it takes to use up the hydrogen fuel at the core of the star, we can figure out how long the star is going to live. So that's a very short and very simplified explanation.
Yeah.
Yeah. So
it's a combination of observing and mathematics this is the physics to figure that out.
We're actually talking several chapters in your local physics textbook. So beware.
I thought I would throw this other image of NGC 4565, the Needle Galaxy, up just to show people that one of the attributes of this view is this second galaxy that looks like it's being shot out of the center of the first one.
Yeah, it does. Yeah,
but it's really neat to see that visually, and it always makes for a good photograph as well. So
yeah.
Another good question came up that is much easier to answer, Gerald. Do all galaxies
You're talking
have a
to the
black
wrong
hole?
guy.
Oh no, this one's easy. Do all galaxies have a black hole at the center? And I think I can answer that. It's believed that yes, almost all galaxies do, at least.
Yes, we believe almost all galaxies have black holes at the center, and like I was saying a while ago, the bigger the black hole at the center, the bigger is the central bulge of the star or the galaxy, and so that's another thing that we can measure, and we'll start making estimates about the size and mass of a galaxy.
And then one last question about black holes.
Okay.
It sounds like a dangerous galaxy to be in with a big black hole, but only at the center. So don't worry about it. Our galaxy has a big black hole at the center as well, and we seem to be doing okay.
Yeah, there's a common misunderstanding about black holes, that somehow they reach out and grab you from huge distances, and that's not the case. You have to be within the right distance of a black hole for it to actually suck you in, and you can actually get pretty close to a lot of black holes and not get sucked in. So fear not. So okay, I got a couple of more images I wanted to share with you. Some more galaxies shot with our telescope. This is the galaxy M51, called the Whirlpool Galaxy, and it is in the process of slowly merging with another galaxy, a smaller galaxy that you can see up here at the top of the screen. And again, this was taken with Nellie, our 36-inch telescope. And once again, you can see these clouds, these dark clouds of gas and dust. And you notice that there's a lot of bright stars, or what looks like bright stars, within them. That's because that's where new stars are forming within this galaxy. New stars form inside of huge clouds of gas and dust. And as they form and as they emerge, some of them can be quite bright. And then, of course, occasionally the old ones die in a supernova, and then they're really bright. One supernova exploding star in a galaxy can put out as much light as all the other stars in the galaxy combined. So when that happens, it can be pretty interesting. And I think I've got one more here. Yeah, here. Oh, actually, two more. So this is sometimes known as the Black Eye Galaxy. It's actually called M64. And another spiral galaxy with a relatively small black hole at the center. And you can see lots of gas and dust close into the center. Why we don't see so much out here, I don't know. But clearly you can see these clouds of gas and dust that are close into the center. And then the last one I want to show you, and again, these are all taken with our telescope at Chabot, is this one. This is called M87. This is a galaxy. It doesn't look like a galaxy, but this is actually a galaxy with a very, very massive black hole at the center. In fact, you may recall a couple of years ago when they were able to get the first actual images of a black hole. It was the black hole at the center of this galaxy. That black hole is very active. When we say it's active, that means it's actually consuming stuff from around it. A black hole can exist without consuming things around it, but if stuff gets close enough to the black hole will pull it in. As it's pulled in, it produces what we call an accretion disk, where stars or planets or whatever it's pulling in gets ripped apart and ends up spiraling its way into the black hole, producing a lot of energy along the way, and often producing what we call polar jets. And in this image, you can actually see the polar jet that is shooting several light years out of the galaxy. So that little streak that you see right there, that's not a smudge on the image or the lens or anything like that. That is the polar jet shooting material out from the central black hole, the region of the central black hole, out into space. And we see these quite often in other galaxies, especially where they have what we call active galactic nuclei, or black holes that are very active at their center. All right. So those are some of the galaxies that we would have been looking at.
Gerald, in this image, at a right angle, angle to that jet, there were two additional galaxies. I wonder if those are interacting with the one in the foreground.
Let me get back to
M87.
that. You mean these two?
No,
yeah,
I think those are actually background galaxies. I don't think they're interacting with M87.
Yeah, I just happened to see them there, and interesting.
So there's one other thing I wanted to show you here that we would have been looking at. We would not have just been looking at galaxies. We would also have looked at globular star clusters. And this is a globular star cluster. This particular one is M13, which we probably wouldn't have seen tonight because it's a little too low in the eastern sky. But each night it will get a little bit higher, and by middle of May, it will be quite high up. This is one of 150 globular star clusters that orbit around our galaxy. Each of these globular clusters has several 100,000 stars. We think M13 has about 500,000 stars in it. And the stars in the cluster all orbit around the center of the cluster, but they orbit in highly elliptical orbits. So rather than nice circles, they orbit in ellipses that go in and come way out and then in and way out again, orbiting around the center of the cluster. But when they're close in, when they're going around close into the center, they're moving very rapidly. When they get way out here, they're moving very slowly. And we can actually measure their orbital velocity by watching these clusters over time. And again, using that red shift and blue shift, Doppler shift concept to actually measure the velocity of the stars. If we know the velocity of a star and we watch it over time and see how much it changes position, we can then use that information to calculate how far away the cluster is, but we can also use it to calculate the mass of the cluster. So a few minutes ago, I said that this cluster has about 500,000 stars, and you may be asking yourself, how does he know that?
We thought you were up late
Yeah.
counting them.
Yes,
That's right.
1, 2, 3.
I caught him
4.
doing that one night.
He's got an app for that. Yeah.
And the problem is, if I count all the stars I see here, I have to multiply by 2 because I'm only seeing the front side of it, right? So actually, what we do is we use that information that we get from watching the stars orbit around the center. It turns out that once you can figure out how long it takes that star to orbit around the center of the cluster, by watching it over time and measuring its velocity and seeing how much it changes from one year to the next by taking images over long periods of time. Once we know the velocity of the star and the period of the star around the cluster, we can calculate the mass of the cluster. So what we do is we actually go through this process. We do it for several stars, and we get slightly different numbers. And so you add them up and you average them and so on. And you come up with a number that represents the mass of the cluster. Well, of course, there can be big stars and little stars in the cluster. So how do we know what the count is? And that's where it gets, there's a little assumption that comes into play. We make the assumption that our sun is an average size star. So we take the mass of the globular cluster that we've calculated by watching the star orbits, and we divide it by the mass of the sun, and we come up with a number. And that is the number. When you hear us say it's got 500,000 stars, what we're really saying is the mass of the cluster is approximately 500,000 times the mass of our sun. So that's how we count stars, quote unquote, in globular star clusters. All right.
See, that's how Gerald does it. When I want to know, I'd say, Gerald, what's the mass of that cluster?
Yeah. He always answers right away, too.
He does. He's got it. Yeah.
Yeah.
But somebody asked a question that I bet you Gerald doesn't have an answer for.
Probably not.
Do you have any idea what happens to things that get pulled into a black hole?
They disappear.
Unfortunately, we don't know.
Yeah, once they cross the event horizon.
Event horizon, yeah.
Once they're past the event horizon, what happens after that? We don't know, except that we know that the mass of whatever that object is still there. Because as the black hole pulls in the mass of all these stars and planets and gas and dust and what have you that are out in space, as it gets pulled into the black hole and it crosses the event horizon, it's adding to the mass of the black hole. And it turns out that the diameter of a black hole's event horizon is directly proportional to the mass of the black hole. So a low mass black hole has a relatively small diameter. For example, if we were to squeeze our sun down into a black hole, its diameter, the diameter of the event horizon rather, would only be about 5 or 6 miles. So as long as you're outside of that 5 or 6 mile range, you're sort of safe. On the other hand, at the center of our galaxy, the Milky Way galaxy, there's a black hole that has 4 million times the mass of our sun. So that means the diameter of the black or of the event horizon is 4 million times at 5 miles. So figure that out. So anyway,
And
what
our
happens?
residents
What we can say is that if someone goes into the event horizon, they will be having an event, and we will not.
Yeah.
It'll be all yours.
Yeah, we can have a lot of fun about a process called spaghettification.
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 Yeah. Because as you approach the black hole, your body gets stretched out because the gravity is so strong. It's actually stronger at your feet than it is at your head, and you start to get stretched out. And astronomers, they're always looking for these very scientific terms, so they call it spaghettification. You get stretched out like a spaghetti noodle. So, all right.
I think we've gotten into the situation that we often see at Chabot, where once one question about black holes gets asked, a whole bunch more seem to follow.
Yeah, that's
So,
right.
One more black hole question.
All right.
One more is, where is the black hole in relation to Earth in our galaxy? Well, you pretty much answered that, describing where Earth was in relation to the center of the galaxy, and that's where the black hole is.
Well, the black hole is at the center of the galaxy. The Earth is not.
No, the Earth is, you mentioned before, about halfway from the center out to the edge.
Yeah. So, if you recall that image that I showed you of the Needle galaxy, which we think may be pretty close to, let me share that again here. I hope I'm going to be able to share it.
I've got it queued up.
If you've got it ready. Oh, wait, I got it here.
Okay, go for it.
Honestly, I've been doing this for 2 years. So we think this is not too dissimilar to the Milky Way galaxy. So you got the central bulge, you've got the disk, and then way out here is the edge. The edge is actually off the edge of the frame here. But we think the sun is about halfway between the central bulge and the outer edge, roughly 25,000 light years from the center. The black hole at the center of our galaxy is at the center of the central bulge. So we're a good 25,000 light years away from it. So that means we're nice and safe. You can there are some images taken of that region. The Keck telescope, the two 10-meter telescopes in Hawaii, a couple other observatories have imaged that region. It's a region that you can see with your naked eye in the summer, like late July, early August. If you're up around 10 o'clock, 11 o'clock at night, if you look to the south, that's for those of us here in the Bay Area. And if you can see the Milky Way, which you can't from the Bay Area, but if you were somewhere up in the mountains and you could see the Milky Way, you look to the south and you'll see that it's much wider than it is, say, looking straight overhead. And that's because when you're looking to the south in late July at night, you're looking right into the center of the Milky Way galaxy. Now, astronomers have pointed their telescopes in that direction, and with a lot of tweaking and what's called adaptive optics and so on, they've actually been able to image the center part of the galaxy up close. And what they see are stars orbiting around nothing. So the black hole at the center of our galaxy is not an active black hole. It's not consuming anything, so it's not emitting any kind of light. But orbiting around it at a safe distance are stars. And because of that black hole is so massive, the orbital rate for those stars is actually pretty rapid. So astronomers have actually been able to take multiple images over time of those stars orbiting around the black hole, piece them together into a little movie where you can actually see the stars orbiting around the black hole at the center of our galaxy.
Yeah, Dave Shaw posted a link to that.
Great,
YouTube,
great.
so
Thank you, Dave. Thank you. That was on YouTube?
Yes.
Okay. Maybe if we can get it over on YouTube or Facebook.
He posted it on Facebook, but it's a YouTube link.
Oh, okay.
I'm sorry.
All right. Yeah, maybe if we could post it on YouTube as well,
I'll see
that
if
would
I
be
can do
good.
that.
Yeah. Okay. Other questions. I see one here on YouTube. If the stars in a globular cluster are all orbiting the center of the cluster at cross purposes and elliptical orbits, do they frequently collide or get thrown out of the cluster? Yes to both. Yes, they do collide. In fact, those collisions often produce what we call blue stragglers. When the stars collide, either one star strips off the outer layers of the other star, or the two stars actually merge. Either way, you end up exposing a much hotter star. If you strip off the outer layers, you expose the hot interior. If you take two stars and merge them, you now have much more mass, and so the star is hotter. Either way, the star ends up in a bluish white color. Because globular clusters are so old, there shouldn't be any young stars in them, or at least we thought there shouldn't be any young stars in them. So when astronomers first started seeing blue stars in globular clusters, they couldn't understand what was going on. Eventually, they realized that it was because the stars occasionally bump into each other. So the answer to your question is yes, they occasionally do. And yes, because of gravitational interactions, occasionally they can throw stuff out of the globular cluster completely. Another interesting thing about globular clusters, you notice how the stars were all very close together. If you lived on a planet orbiting around one of those stars in the cluster, you wouldn't have a nighttime because there would be so many stars so close to you that they would just light up your night sky. The sky might be a little dark, but it would be like having a night sky with 100 full moons in it. So you wouldn't get to see the Milky Way very well because there's just too much light pollution in the sky. And there's an interesting story, I think it was written by Isaac Asimov, called Nightfall.
Yep.
And it's actually a short story. And it's about a civilization living on a planet orbiting a star in a globular star cluster. And I think it's once every 1,000 years, everything lines up just right so that they get a truly dark night. And it's just this once every 1,000-year event. And that the story is about how the civilization is responding to that upcoming totally dark night. So the book is called Nightfall. Check it out.
He wrote it in 1941.
Yeah.
Yeah.
All right. Any other questions? All right. Well, do we have anything else we want to share, guys? Wait. Yes, I have one other thing to share.
The comet.
The
Comet, yes.
Well, okay.
Or was that what you were going to
That's
talk
what we
about?
want you to share.
Okay. We'll do the comet first. Actually, two things we need to talk about related to comets. First of all, the big comet, the Don't Look Up comet.
Oh, no.
So you may have heard recently that astronomers have found a huge comet orbiting around the sun. And there have been some news articles saying this is a huge comet and it's coming towards the Earth and all that good stuff. Not true. It is a huge comet. Most comets are somewhere between 1 and 5 kilometers in size. So, it's kind of big, but not real big. This particular comet is 120 kilometers in size. So it is one huge chunk of ice with a lot of dirt and rock embedded in it. It is coming in toward the inner part of the solar system, sort of, but it's not going to get anywhere near Earth. In fact, when it's closest to the sun, it will be farther from the sun than the planet Saturn. So it's coming in closer to the sun, but it's not headed anywhere close to the Earth. So don't worry, put your hard hats away, everything's cool. Okay. It's kind of dramatic because of the size. This is by far the biggest one we've ever seen, but it's in terms of its orbit and any possibility of us seeing it naked eye, that's not going to happen, and that's certainly not going to be any threat to the Earth. However, there was another comet called Schwarzmann-Bachmann 3. Easy for me to say. Also, no, I think it's P73.
73P.
73P, yes. This is a comet that orbits around the sun, or what's left of it is orbiting around the sun every 5.5 years, roughly. And in 1995, it broke up. As it got close to the sun warmed it up. Comets, the nucleus of a comet is mostly ice with a lot of rock and gravel and sand and dust embedded in the ice. As it got closer to the sun, some of that ice began to sublimate. It turned into a gas, and eventually the comet broke apart into numerous smaller pieces, scattering a lot of dust and particulates along the way. And all that debris has been orbiting around the sun ever since 1995. Well, it turns out that there is a reasonably good chance that on the night of May 30th, for those of us in the Bay Area, at about 10 o'clock at night, the Earth will pass or actually intersect with that stream of particles. Those particles are going to be traveling relatively slowly compared to the Earth because their direction of motion actually puts them a little bit behind the Earth. So they're catching up to the Earth. So relative to the Earth, they're not moving very fast. This is a little bit different than the typical situation where the Earth is plowing into a stream of particles left behind by a comet. In this case, it's the other way around. The stream of particles is plowing into the Earth or chasing after the Earth. We're not sure what's going to happen. Some astronomers think we won't see anything. Some astronomers think we will see a moderate meteor shower, not a lot of bright ones, only a few meteors per hour. And then some astronomers think we will have a meteor storm where you're seeing one right after the other across the sky.
Fingers crossed.
Yeah. So again, the time to look for this, if you're here on the West Coast, California, West Coast, the time is approximately 10 o'clock p.m. on the night of May 30th. If you're in Europe, it's already going to be after midnight so early in the morning on the 31st. You're actually less likely to see it in Europe because of the angle at which these particles are going to be coming at the Earth. If you want to know where in the sky to look, there's the star Arcturus. Arcturus is one of the brightest stars in the night sky. It's a bright yellowish orange star. And on May 30th, it actually will be quite high in the sky at around 10 o'clock. It'll be one of the brightest stars in the sky, and it'll have a distinct yellowish orange color. And right next to Arcturus is what we call the radiant. It's where all these meteors will seem to come from. So if you have clear skies on the night of May 30th, go outside, find Arcturus in the sky, and just kind of generally watch the sky. Don't just stare at Arcturus, stare at that whole region of the sky, because meteors take up huge streaks in the sky. They're not little points of light. And if you're lucky, we'll have a meteor storm, and it'll be quite spectacular. If you're sort of lucky, we'll have a few meteors, and you might get to see them. And if you're unlucky, you won't see anything. So tell us what happens the next day.
There you go.
All right.
Is that it?
Any other questions?
Before
Yeah,
we
we'll take
stop,
some questions.
I want to clear up one misunderstanding that somebody had. Now I got to go back and find it here. Kat says she lives in Michigan and says because she's in rural Michigan, she can often see the Milky Way. She'll look for the black hole. I just want to caution you, don't look for the black hole. You won't see the black hole. You can look for the center of the galaxy and see the bulge in the Milky Way at that point, but you won't be able to actually see the black hole.
Yeah, you need a very, 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 very powerful telescope with what's called adaptive optics on it. And you need a lot of patience. And you're not going to see it with your naked eye. You're not going to see it with binoculars.
And even with that, you're not actually. Yeah, you're not actually seeing the black hole. That's kind of like
you're seeing the stars around
the region around it.
Yeah, right.
Wouldn't be a very black hole if you were able to see.
Exactly.
People just love black holes. I don't know what it is about them.
Well, they're weird.
Here's another one. Are there rogue black holes floating between the galaxies?
Yes. There's rogue black holes floating around the galaxy too. So
yeah, maybe even within some galaxies.
You wonder where your socks go.
I thought that was the dryer.
All right. Any other questions?
I think that's it.
Yeah.
All right.
Well, thank you all for joining us tonight, and thank you for your donations, and thank you for putting up with us and our frequent technological failures.
Yeah.
We'll try harder next time.
This is live science.
Well, I think what it's all trying to tell you, Gerald, is you got to upgrade to Windows 11.
I'll tell you what, when Windows 11 lets me put the taskbar on the right instead of at the bottom, I'll upgrade.
Yeah. I'll print out a photo of one and you can stick it on your screen. All right, everyone. Alrighty. You take care and we'll see you next month.